Hey, this is Mr. Mitchell. Recording here on Zoom. I recorded it on Screencast-O-Matic for this lesson, but for some reason it won't save. So I'm actually going to just play the Screencast-O-Matic for you, because it has all the important information on it. It's recording through Zoom. We'll see if this works. Give it a shot. If you have any questions, let me know. You're not going to see me talking, but you'll see the video playing. So.
Hey, pre-calc students, Mr. Mitchell here. We're going to take a look at exponential functions and their graphs today. Got some notes here at the top. Just be aware of. When we look at e to the x, that's called the natural exponential function. We also have a natural log function that we'll deal with in the next section. But this section is all about exponential functions and graphs. So just some information up here on how to use certain things we need to be aware of. Compound interest formula. This is if you put money in your bank, how much can you expect after so many years? So we just need to be aware of certain variables and what they mean. We have the compound interest formula for a year, for yearly amounts, and then this is for continuously compounding. This is more, not necessarily for banks. This is more for like bacteria growth and decay, but it could be used for money. So A is for the interest earned. That's the amount of money you make off of your bank or the bacteria that's grown or decayed. P is the principal or the starting amount of money or bacteria or something else. R is the interest rate or the rate of increase or decrease. N is the number of times compounded. If you look at the continuous formula, there is no n because compounding continuously isn't a specified amount. Continuous growth or decay concept. And T is the time. So those are all the variables. All right. So first we're going to evaluate exponential expressions using the calculator. So I have my calculator handy. So we have 2 caret to the negative 3.1 power. 0.1166. How many places should you go to? Well, let's see. Do the directions tell us? Round to the thousandth place. So I need 3 decimal places, so 0.116. Go. 0.116. Now I need 2 to the negative 5. I have 2 caret negative, and then the pi button is right here on the blue second. So negative 0.11. 0.113. All right, so that's how you type stuff into the calculator. It's always important for us to look at that. So we're going to graph some things. So we can use our calculator. Let's do that the first one. We'll try to figure out what some patterns are. We learned about transformations before. So 2 caret x, 2 to the x. And we're going to graph that. And anytime we don't see anything, we always can go to our window and start over. So our max, our exponent is negative 10, our max is 10. Make the x scale 1, make the y min negative 10, y max 10. So there's our exponential growth equation, because it is a growing. As you go from left to right, it grows. So when I come back to my graph, again, I know where things are going to be. It's going to go through 0, 1. That's going to be my y-intercept. And it's going to kind of look like this. That's a little better draw. Okay. So our domain for any exponential equation is always everything. Negative infinity to positive infinity. It's going left forever. It's going up right forever. Doesn't matter whether it's going up or down. It's going left and right forever. So even these equations, I can come over here right now. Anytime I have a exponential equation, my domain is always everything. I can plug in anything I want. Any number that's real, any real number. I can plug in anything I want. So now I need to look at the range. Well, where does it go up forever? Yes. Does it go down forever? No. Okay. So my range is going to be limited going down, at least on this one. So my range is everything up with a parenthesis. Where does it go down to? Well, it doesn't cross the x-axis. So that means it's 0 to infinity, not including 0. You can't get 0 out of this. You can't also get a negative out of it. You can plug in negatives, but you're never going to make a negative number. So that's our range, 0 to infinity. It also has a horizontal asymptote then, since we know we can't cross 0. So the asymptote is y 0. And as you go from left to right, does the graph go up or down? Nope, so that means it's an increasing function. But coming over here, what do you think this graph does? Well, we can check it out on the calculator, make that comparison. So let's go to y. Graph 4 to the x. And it looks pretty darn simple, doesn't it? So, again, knowing your transformation rules from 4, this equation is going to go through 0, 1 again. All it's going to do is it's going to explode up a lot. So it still has the horizontal asymptote at the same place. So the y equals 0 is still there. Our range is still 0 to infinity. And our y-intercept is still 0, 1. So what really changed? Just how fast it grew. So if you think about it this way, this is really a horizontal compression by 1/4. It's really what it amounts to. You are smushing the graph and making it tighter. But you didn't move it. It's still anchored at the same place. Okay? So then what happens if the graph goes from left to right? It's still going up. So it's an increasing function. All right? So now looking at this one, knowing our transformation rules, does the graph move left or right, up or down? Does not. It's staying in the same approximate place. We're going to have another horizontal asymptote. Anytime you have an exponential, you have a horizontal, so it's y equals 0. The range isn't going to change here. It's going to be the same thing, so it's going to be 0 to infinity. What does a negative on the inside mean? Because that's what this is. A negative on the inside, what does that do? Well, we said it didn't move, so it's still going to be going through 0, 1. So that's going through this point here. A negative on the inside reflects it. A negative on the outside reflects it up and down. A negative on the inside reflects it this way. So our graph, look, something like that. So these two are the same thing, except for they are reflected over the y-axis. This is a decreasing function. How do I know that? Well, as you go from left to right, what is the graph doing? It's going down. It's going closer and closer to 0. So you can guess what this one looks like. It's going to look like this one, except for reflected. So we're going to have another horizontal asymptote at y equals 0. Our range is still going to be 0 to infinity. We're going to have a y-intercept of 0, 1. Nothing changes except for it's reflected over the y-axis. Now, again, it's going to be taller than one we just drew. Again, it does go through 0, 1. Trying to draw this with my pen is sometimes difficult. And we're also a decreasing function. As you go from left to right, the graph is going down. Okay? So for these one-to-one properties, we're just looking to see what on the right side makes the left side, what makes them equal. So what does 9 in terms of the base 3? Because notice the base is 3. You need to get this. So 9 is actually 3 squared. So what does x have to be to make it true? Well, really, you can probably see what it is right now, but you've got to set the exponents equal to each other. And then x turns out to be 1. Over here, what number can we raise 1/2 to make it 8? Well, if you know anything about exponent rules, how do you make a fraction into a regular integer? You need to make it negative. So some of these you can do by just kind of figuring out trial and error, those you set equations up. So what power does 1/2 need to be to make it into 8? Well, if it were 2 to the x, how would you make that into 8? Well, x would have to be 3, right? 2 cubed is 8. But it's 1/2. 1/2 is 1/8. How do I make 1/8 into 8? Make the exponent negative. So if it's 1/2 to the -3, first you flip it, and then you cube it. So x equals -3. Now we're down in here talking about transformations. I already mentioned this before, but where is the number and what does it do? Is it on the inside? It means something left and right. On the outside, it means something up and down. Here's a +1. What does that do? +1 is either moving it up 1 or left 1. Where is it at? It's inside, so it's a horizontal translation, left 1. Where's this number? We're going to move it. We're either moving it down 2 or right 2. Where's the -2 at? It's on the outside. It's a vertical translation, down 2. Where's the negative at? It's on the outside. Something up and down is happening. What is a negative on the outside? It's a reflection of the x. And then what's a negative on the inside do? It's a reflection, y. Here's some other calculator questions. So, e to the -2. E is a naturally occurring number. It's kind of like pi. So let's take a look. E to the negative, was it -2? Yep. E to the -2, 0.135. I think we're still going to 3 decimal places. 0.135. E to the -1. Again, these are calculator questions, so just need to do them that way. -0.2718. -2.178. E to the 0.25. To the 0.25. 1.284. 1.284. And then e to the -0.3. -0.3. 0.741. 0.741. So that's calculator computations. So now here we go with compound interest. The total $12,000 was invested. This is our P. At an annual interest rate, so R is going to equal 0.09. Let's change the percent into a straight decimal. T is 5. If it's compounded quarterly, that means N is 4. Monthly, N is 12. Continuously, N is infinity, which means a different formula, the PERT. Okay? PERT. So here we go. Got our formula. A equals 1 plus 0.09 over N. Over 4, sorry, we know what N is. N is 4. To the 4 times 5 power. So now we need to take our calculator. So now we just need to use our calculator. So we have 1 plus 0.09 divided by 4 to the power of 4 times 5. I'm going to type it in all at once, exactly the way that it's written, exactly the way it's written in the formula. Okay. Oops, I forgot my 12,000. So I need to put my 12,000 out front here. I forgot to type that in my calculator. I could put it at the end here. So then it's time. Preferably you put 12,000 at the beginning. Okay. So 18,726 You can also see I typed it in the other way. Doesn't matter whether you multiply before or after. So $18,726.11. $18,726.11. Okay, so that's compounded quarterly, 4 times a year. So now
we're going to find the answer in terms of monthly. So now we need to take our formula and we're going to need to plug in 12 where there was an N. So in our formula, everything else should stay the same. So bear with me as I'm setting up my pen here so that I can write. Beeping at us. So we need to get, that's not working. Well, I guess we'll just have to do it in part 2 of our installment. So I'm having trouble writing on this. Not gonna let me write on that, but it probably will let me write on this. Here we go. So we're gonna take A, we're trying to find the amount that's in the account. We start with $12,000, that's how much, so we're just comparing if they compound it monthly instead of quarterly. Most banks compound monthly. So we plug in 12,000 for our principal. Formula has 1 plus 0.09 over 12 is N. And then that is to the 12 times 5 power. So then we got to type that in our calculator. So we got 12,000 times 1 plus 0.09 divided by 12. And then that is to the power of 12 times 5. $18,788.17. $18,788 and double check 17 cents. 17 cents. So there's the amount of money that is compounded monthly. So if you notice, that's more money. So you should tell your bank to compound it more. If we did daily, it would be a little bit more. So most banks aren't going to compound daily. In terms of money in banks, monthly is probably the best you're going to get. Some do it quarterly. If you're talking about stocks, they don't usually grow on a set certain amount. But stocks change continuously, but that's not a straight equation versus a bank account. So now we look at the letter C. We have continuously. So we're going to do N as infinity. So you can't plug infinity in here. So we have a new formula. It's P equals, A, that's the wrong formula. A equals PE to the RT. I wrote it wrong first time. So we're trying to find the amount that's going to be in our account. We put in our initial amount of 12,000. E to the 0.09 times 5. And then that should be our amount. So we're going to go 12,000 times the E button is the second E there. And that is to the 0.09 times 5. And notice it's a little bit more than compounding monthly. So we come over here to our 18,889. Was that right? Did I copy that down right? Nope. I thought it was more. $19. Sorry about that. So let's change that to 19. And how many cents? 74. 75, we'll round that up. Okay, so you can see compounding more often is going to give you more money. So you should tell your bank to compound as many times as they will. Not that you have much say in that matter, but it'd be nice if you had a little pull with that. So, all right, so we have radioactive decay. So here's a little formula. The half-life means it takes that many years to cut in half. So if you started with 10, you would end up with 5 after almost 1,600 years. That's a long time, but that's how long it takes for a lot of our radioactive material that we are using to decay. That's why a lot of proponents of nuclear energy are very against it. I guess you're opponents, not proponent. If you're a proponent of nuclear energy, there's not a lot of waste in it. It's just the waste that there is doesn't go away for a long time. You and I will be long gone, and there'll still be nuclear waste from the nuclear power plants. It'll still be decaying at a very, very, very slow rate. Okay? So after each 1,600 years, 1599, half will be there, and then another half, and then another half, and another half. And so that's kind of the way it works. So what is the initial mass when t equals 0? So if you plug in 0 for t, you get 0. What's anything to the 0 power? Not 0, it's 1. So it's 25 times 1/2 to the 0 power, which is 25 times 1. So there's 25 grams. That's how much you're starting with. 25 grams is not a lot, but it's enough if it's radioactive material. So how much is present after 2,500 years? So it should be half of 25, right? Because 1599 years, it'll be half of 25. It'll be 12.5. So it's going to be less than that, but it's not going to get cut in half twice. So it should be somewhere between 12.5 and 6.25 grams, somewhere I would think. So we're going to take our calculator. So we're going to go 25 times 1/2 to the 2,500 divided by 1599 power. I believe I copied all that stuff right. Before I hit enter, I'm going to check it. Yes. And then I'm going to hit enter. 8.45, 8.46 grams. So 8.46 grams. So again, what did we do? We plugged in 2,500 here. So after 2,500 years, there will be that much left. So that's still a long time before it will decay much more. So it's a very slow decaying process. It's not like your compost, if you have your backyard, or when leaves decay in the woods. It's a much, much slower process than just a year or two. So if you have any questions, let me know and we'll work on it.